Hi everyone, my name is Paul, and I'm a PhD student in Carnegie Mellon University. Today, I'll be presenting some of my recent work towards building real-world social intelligence. AI has made significant progress in physical intelligence, the ability to understand and manipulate real-world objects, and digital intelligence, the ability to comprehend data on digital mediums such as the internet. In my opinion, the next milestone for AI will be to understand social intelligence, a trait natural to humans but a grand challenge to current machines. My research therefore builds towards socially intelligent AI that can comprehend human social cues, intents, and affective states, engage in social conversation, and understand social norms and common sense in order to maintain a rich level of interaction with humans. Building social AI will have major applications in understanding multimedia content, such as online videos, building intelligent personal assistants that can engage people through social interactions, and eventually, interactive robots that can monitor human behavior to understand the types of help people need and offer their assistance in schools, hospitals, and the workplace. Underlying these desirable applications of social intelligence are fundamental algorithms for multimodal perception and multimodal interaction. Underlying human social intelligence is human communication, a structured system of social signals used by us to convey our intentions through verbal and nonverbal channels. Perceiving multimodal communication from a human speaker therefore involves comprehending these social cues, intents, affective states, personalities, and references to the broader environment. Interactive social intelligence then involves modeling the long-term interactive loop between social perception and action. After perceiving human communication, social intelligence agents should be able to communicate through human behaviors and take actions in some embodied environment. In order to enable multimodal perception and interaction, there are underlying foundations in multimodal machine learning that need to be solved, involving the fusion, representation, alignment, translation, and co-learning from multimodal data. While prior research towards social intelligence has indeed made impressive strides in effective computing and dialogue systems, a big thrust of my research is to aim to bridge the gap towards real-world deployment in such important human-centric areas. Therefore, some of my research has also focused on developing algorithms that improve the robustness, fairness, privacy, and generalizability of these current multimodal methods in these social intelligence contexts. My research has also focused on some actual real-world applications of social intelligence and multimodal models in healthcare and education. In this talk, I would like to give just a glimpse of some of the research I have done towards building socially intelligent AI. Some of my research has built towards large benchmarks for multimodal learning, such as multimodal affective recognition, where the goal is to perceive human behaviors and social cues from human speech, a multimodal signal spanning text, as well as how humans say it, such as the audio, tone of voice, and different facial gestures. We have built and created data sets that shows large diversity in speakers and topics, and ensure that there is a set of accurate and high-quality annotations to enable accurate machine learning from human behaviors. Recently, we also created a large-scale standardized benchmark called Multibench, which contains a diverse set of 15 datasets spanning 10 modalities and testing for more than 20 prediction tasks. These datasets are sourced from a set of 6 important research areas that are all important for social intelligence, such as affective computing, healthcare, robotics, and HCI. We believe that Multibench can enable the next generation of standardized, reliable, and reproducible large-scale benchmarking of multimodal models. Multibench is also designed to reflect real-world requirements of multimodal models because it enables us to holistically evaluate performance across domains and modalities, complexity during training and inference, and also the real-world robustness to noisy and missing modalities. Using some of these large-scale benchmarks, we've also designed methods that are suitable for noisy and missing multimodal data. Some of these insights involve using tensors to represent multimodal interactions and restricting their rank to ensuring smoothness over modalities and time, and therefore smoothing out the noisy and imperfections that might exist in different modalities. We have also designed new generative models of multimodal learning that enable the learning of representations that are factorized into multimodal specific representations and joint multimodal representations. Each of these factors are designed to model one particular variation in the data, which we find to be more effective and robust than entangled representations, as is commonly used in current literature. Designing such a generative model also allows us to perform better interpretation of trained models, and also allows us to perform inference of noisy and missing modalities, and therefore leading to more robust multimodal learning. We have also designed several new paradigms of learning multimodal representations. While classic ways of learning multimodal representations involve taking both language and vision and putting them both through a joint model, we find that learning representations through translation from language to vision, also results in intermediate representations that are very useful for prediction. But this comes with a huge benefit, which is that only language modality is then required at test time, which means that a model is completely robust to any noise and imperfections in the visual modality. We show that this method is as strong as using both language and vision as the input, but at the same time, much for sure being robust to the visual modality during testing. In addition to robustness, a big thrust of my research has also been to ensure the fairness of these methods when deployed in the real world. Machine learning methods are shown to have a risk of exposure bias due to imbalanced data sets, which is especially true when human-centric social data such as text and speech are involved. Models trained on this biased data have then been shown to amplify the underlying social biases, especially when these biases correlate with your prediction targets. Some of my research has proposed new methods to mitigate these biases in the geometry of pre-trained sentence encoders such as BERT, while ensuring that BERT retains its performance on downstream tasks. I've also extended this work to explore ways of measuring and mitigating social biases in pre-trained language models in a generative sense, such as GPT-2. And this has been able to make these language models more safe and controllable. Both of these methods of mitigating biases in sentence encoders and language models are only done through a post-processing step, which means that you do not need to further train a language model, and therefore makes it more efficient. To finish my talk, I would also like to share a very nice ongoing collaboration with the University of Oregon, Columbia University, and the University of Pittsburgh. This project is on using multimodal models towards real-world mental health assessment. This is an important problem because mental health illnesses can have a damaging permanent impact on communities, societies, and economies all over the world, especially in adolescents, because adolescents are often late in seeking professional help. However, intensive monitoring of behaviors by adolescents' natural use of smartphones can actually help to identify real-time predictors of mood as a proxy of suicide risk. To do so, we have analyzed the recent data set of mobile behaviors collected from adolescent populations at different levels, different risks of suicide. This unique data set presents us an opportunity to investigate a different medium of NLP through typed text. And this presents new challenges beyond conventionally studied written and spoken forms of text. Our paper proposes several multimodal models to process typed text for mood prediction. However, we also find that these models often capture private user identities in the intermediate representations when predicting mood. Therefore, we have taken a step towards privacy-preserving learning by proposing several approaches that are able to hide user identity while remaining predictive of daily mood. By combining multimodal learning with privacy-preserving learning, we're then able to push forward the performance and privacy frontier. So I hope I've motivated why it's important to study social intelligence, and more importantly, several shortcomings of several machine learning and multimodal models that make them as of yet unsuitable for real-world deployment. But I plan to push towards these directions in the future, and I hope that some of you watching this will be interested in these directions as well. And all of this work could not have been possible without an amazing group of collaborators, both at CMU and also at industry and academia. I'm really, really grateful to their advice and collaboration through all of these projects that I have done. If you're interested in some of my work, Definitely do check out my website where preprints of all of the work is available. And feel free to shoot me on email or Twitter if you have any questions about my work. More importantly, all of the data sets, code, and benchmarks that I've presented are also publicly available through my GitHub. So definitely do check those out if you're interested. Thank you.